everyone. Today, we are honored to have Dr. George Karniadakis from Brown University talking about his research on automatic discovery of algorithms and neural architectures in scientific machine learning. So George is from Crete, Greece. He's a member of a National Academy of Engineering and Vannevar Bush Faculty Fellow. He received his master and PhD degree from Massachusetts Institute of Technology in 1984 and 1987, respectively. He has been worked in Stanford, Princeton, and now he's become a full professor in 1996. He continued to be a visiting professor and senior lecturer of MIT, as well as affiliated research scientist at Pacific Northwestern National Lab. He's an AAA fellow of the Society for Industry and Applied Mathematics, fellow of the American Physics Society, fellow of the American Society of Mechanical Engineers, and associate fellow of the American Institute of Aeronautics and Astronautics. He received the SES GI Taylor Medal, the SIAM ACM Prize for Computational Science and Engineering, the Alexander von Humboldt Award in 2017, the SIAM Ralf E. Kleinman Award, the Tinsley Oden Medal, and the CFD Award by the United States Association in Computational Mechanics. His H index is 184, and his citation now I've checked is almost 130K by this morning. So we're great honor to have George to give us a talk, and the floor is yours. Thank you.
Thank you. I asked Listen not to say any of this, and just to say that I'm from Crete. I always require that when I give my talks. If you don't know where Crete is, you can look it up. So I want to talk about a new subject. Actually, this is the first time I give this talk. Typically, I talk about physics and for machine learning, but today I want to talk about discovery, automatic discovery of algorithms and neural architectures. And I want to start with this movie that shows what is perhaps one of the most noble endeavors in scientific research, and that is to discover equations. So you all take courses, you know the Maxwell equations, you know maybe the Schrödinger equation, you know the Navier-Stokes equations, and this is the Lorentz equation. So the reason that these equations have names because these are genius. Took them long time, historically, to decades to come up, or centuries, to come up with these equations. So in terms of scientific acceleration, discovery, and acceleration, scientific discovery, the question is, can we do better? Can we discover our own equations for the problem that we're studying? And then we can use it in other domains. So for example, in the Lorentz equation, if you have noisy data, can you find the governing equations? And this is what it's the last 10 years, there have been several publications combined with machine learning and neural networks to show that indeed this is possible. And here are some examples of equations that have been discovered. And from data, in other words, you don't argue, you don't do the physical modeling, you use data. And here's an example. This is one of the first papers that appeared in Science in 2019 on symbolic regression. People did experiments on a very simple experiment, a double pendulum. So you measure the amplitude and the accelerations of the angles of the two vibrating pendula, and then you can obtain directly the Hamiltonian from that. If you have the Hamiltonian, of course, you can have the equations of motion. So that is an important paper because it sparked a lot of interest in this type of thinking. Can I use data, just data, to automatically discover new equations? So people have now rediscovered, let's say, the Lorentz equations and other Schrödinger equations and other equations. You can do that with basically methods of regression. Could be even linear regression, like a library called Cindy, or it can be done with nonlinear regression, like physics-informed neural network is something that we have done. But today I will not talk about that. I want to talk about if we can discover equations, can we also discover algorithms, new algorithms? So imagine you're sitting there and you play around a little bit, and then you have your own algorithm named after you. So I will give you a little bit of a background. It's kind of basic background. See my cursor. Yeah, I see my cursor. So, I will explain two basic algorithms, which are over 100 years old. You probably have learned it in your linear algebra course. And that is the Jacobi and Gauss-Seidel algorithms. So I will assume that these algorithms come from discretizing a differential equation that I describe here as L equals F, L of U, in K some parameters equal F, and then some boundary conditions. So you discretize with your favorite method, and you end up solving a linear system. No matter what we do, when you deal with PDEs, you solve a linear system, and that's sort of the bottleneck, how fast you can do it. In these old methods, classical methods, I said, we break up A, the matrix on the left, into two parts, M and N. M will be the preconditioner. We bring it on the right hand, on the left hand side, and then we invert it. For Jacobi, M is simply the diagonal. It's the oldest algorithm around. And then for Gauss-Seidel, the method that was used until in the 70s, is the diagonal and the lower triangular matrix. So basically, you have a fixed point iteration, and you just guess the answer. And then through this construct, you improve the answer every iteration, but it's a relatively slow method. That's what it used to work until the 70s, as I said. And now in the 70s, there was a big breakthrough. It's still the state of the art, the SOTA. It's the multigrid. Now, multigrid turns out not to be a new algorithm. It's really the same algorithm, but applied to different grids. And I will explain what that is. So multigrid is you have one grid where you solve your equations, then you project it down to a coarser grid and a coarser grid, and then the problem is very small, you solve it with a direct solver, and then you upscale with interpolation. So you have a restriction and an interpolation operator. But basically what you're doing is applying Gauss-Seidel or Jacobi, these old methods, at every step. So why I'm saying this? Because, as I said, Jacobi was invented in 1840. Gauss-Seidel was invented in 1874, and then took 100 years to use these methods properly, where you match the method for the right grid. So it's really a meta solver. You can think of having some basic blocks, and then you use them creatively. But that's all the commercial codes. Everybody's using this multigrid is the state of the art. So this is just an example of an algorithm and its evolution, how it's actually you develop an algorithm, taking bits of information or existing algorithms and create what I call a meta solver. Hope that's clear. But that took 100 years. So can we accelerate from 100 years to 10 minutes? That's the question. So now what was good and what is bad about these classical algorithms, they call it relaxation algorithms. If you look at the solution here on the upper panel A, and you decompose it into its eigenmodes, you see that these algorithms, these relaxation algorithms, that's why they're called smoothers, are very good in smoothing out the high frequency content. So for example, look at mode 1 versus the higher mode here, and I have two differential equations which I discretize and I solve the corresponding linear system. Here, if I plot the error versus the number of iterations in each one, you see mode 1, which is the simplest mode, right? Just a parabola, is the hardest to capture, hardest to go to 0. On the other hand, the higher modes, that very, very rough, high frequency content, they converge very, very fast. So you have a non-uniform convergence from these classical algorithms. So they like to smooth the high modes, but they have hard time with the low modes. Okay, so that's well known in numerical analysis. We study, we show that, but you can see it here. In fact, in the equation on the right, mode 1 diverges. You can see that slows down the whole thing. It's because the simple modes are the troublemakers. Now, let's go to neural networks. In neural networks, we have something called spectral bias, which is exactly the opposite. Here, I plot a function on your left, and then its corresponding Fourier spectrum on the right. And you can see I have these points. If I play the movie again, go back, you can see what happens. The neural network is this red line. It sort of captures the low frequency first on the left. Then it tries to capture the high frequency. You can see that on the Fourier spectrum, the long tail is a high frequency. So in some sense, it's complementary to what I just told you, and that is called spectral bias in neural networks. In other words, neural networks are better with the low frequencies as opposed to high frequencies. These classical methods are very good in high frequencies compared to low frequencies. Is that clear? So out of this, we can actually combine the two and say maybe we can have a meta solver, which is very good, and we can call that the fastest solver on Earth. Let's see if we can accomplish that. So, but before I go to that, I want to give you the numerical analyst's viewpoint of a neural network. The computer scientists define a little differently, but I want to look at this as follows. Let's say you have a neural network from left to right, x1, x2 are two inputs, and then LL here, the last layer, is the output. I can write the neural network. The neural network approximates a function. Everybody should know that. Data in, data out, a neural network approximates a function. So how you approximate a function, you write as a sum of the last linear layer. In neural networks for regression, the last layer is a linear. So you have these linear known coefficients, W, and then times a basis, and this basis phi is actually the basis that the functions that you find in the last hidden layer, which are all the neurons. Every neuron corresponds to a basis. If you take a sum of that, you see that you have a complete basis. And in fact, in this form, this function approximation is very similar to what we have, let's say, with Fourier series. With Fourier series, we have a sum, some coefficients times a basis. The basis there e to the ikx. For finite elements, the basis will be some polynomials. But it is, in that form, its neural network is nothing else, but just another numerical method, if you like, that we approximate functions using weights, W's, and bases. The difference is that in neural networks, the basis is not prefabricated. It's not exponentials and it's not polynomials. In fact, it should not be polynomials. It's some basis that is computed on the fly, depending on the data. So in some sense, it's the optimum basis. That's why I call the adaptive basis, because you change your data, or the physics, for example, or the base will be the function. You change the basis automatically. So that's the adaptive basis viewpoint for a neural network. I'm not sure if you have ever seen this, but it's a very useful viewpoint to understand better what sometimes the computer scientists make it look like magic, but there's no magic. Okay, so I want to go now to something else that is perhaps a little more advanced, but much more useful. And that is, as I said, neural networks take data in, data out. So what maps data to data is a function, as we just said. So that's a neural network. And that is what I have here in some benchmarks, NIST and ImageNet and so on. And of course, neural networks are very successful in imaging. What you map is really a finite dimensional space to a finite dimensional space. Now imagine you have as inputs functions, not data, but functions. And then as output, you also have functions. So I need a mapping between functions to functions. What is that called? Called operator, for example. Like a derivative is an operator. Derivative takes as an input a function and produces a function. An integral is an operator, indefinite integral. Or an equation itself, a whole equation, no matter how complicated it is, it's really an operator. A black box is an operator. Put some distribution in and you get distribution out. So technically it's a very different thing, because now we have to map infinite dimensional space to infinite dimensional space instead of this. So anyway, this turns out to be very useful because instead of solving the problem every time, you can basically pre-train your operator to solve for a plurality of conditions, not just one condition. If you do autonomy, for example, that will be very useful because you look at all possible conditions. And then you have solutions for that. And then after the training, you can really forecast do inference in real time, not almost real time, in real time, less than a microsecond of inference, because it's all pre-trained. It's like the foundation models. When you use ChatGPT, it's exactly that. You don't train, you train directly, but it's already pre-trained and becomes smarter as you interact with it. So the same idea. So this is what I said. It's inspired by a human neuron. In a human neuron, you have the dendrites or the branches, and then you have the soma, where the computation is done. It's called the trunk. And then you have this axon, and then you have a synaptic output. Here, now we use two neural networks. One is on the left, which is the input, and one is on the right. That's the trunk. So I have the branch, the input, the trunk, which is the soma, where the computation is done. That trunk is very important because it will give us a basis. I already talked about basis with respect to which the operator can be expanded and approximated. And then they work in sync here and to find the output. So here I have a bunch of functions, which could be inputs. And then you have the solutions of these operators would be the outputs. But these differential equations here are actually the operators. So what I'm saying is that we can actually discover these operators from data. Okay, so in some sense, that's already a discovery, automatic discovery. So there's a theorem that says that there is a universal approximation of operators. I'm not going to talk about it here, but this is what the mathematical construct is, that this G, which is the operator I want to approximate, of U, which is a function, so G of U is a function. For functions, it's very similar. Y is the output space. It's a double sum. And this is for a single hidden layer. So you can see this is a trunk here. Sigma is activation function. And this is another summation here. U is a function, so you sample it. That's how you project your function into a finite dimensional space. And then sigma is again the activation function. So this is the branch, this is the trunk, and these are the two neural networks that I show you work in sync to give you. So a depot net, as I said, can be thought of as a foundation model, and it can discover all these equations. For example, I have a bunch of equations here, something called the Darcy flow, which is for in porous media, elasticity model in solid mechanics, the Brusselator diffusion reaction system in chemical engineering. So notice here that you can train it also in a domain with a square, but actually then you can target a domain which is triangular. Here, a domain of one hole, you can target domains and so on with very little transfer learning. Here, the last one, you learn the foundation model for a limit cycle, and then you transfer to a stationary point that is shown on the right. So these foundation models are very, very important. As I said, you can think of very similar to ChatGPT. In fact, we start using ChatGPT to do this type of mathematics problems now using transformers. So I also talked about the resemblance of these dendrites. And the point is here, you can use any neural network. You can use a graph neural network or spiking neural networks in the branch, and you can do the same thing for the trunk. You can have graph neural networks, as I said, or fully connected neural networks. Or if you do imaging, you can do convolutional neural networks and so on. So it gives you a plurality of different neural operators that map functions to functions. So what does that mean? Functions is that imagine you're solving a problem with very different operating conditions. You can input all those operating conditions in the pre-training, and then you have the solutions. So when you try to apply that operator, you do that at zero time, at real time. That's very important for applications. So there are other operators, like the Fourier neural operator here, for example. It has a starting point is based on, those of you who know what the Green's functions are. This is some sort of linear superposition of solutions with Green's functions here, but you can generalize that with a kernel and then add another component here, which is trainable. So this kernel is trainable, W is trainable. And the question is, how do you do this convolution of the integral very fast? Convolutions, you have Fourier methods, Laplace transforms, wavelet transforms, and so on. So you can develop all sorts of different operators, which are kind of different now. The basis is sort of fixed. And then if you have an input V, you can lift it up in high dimensions, and then you stack up different Fourier layers, and you can see here how you use Fourier to compute the convolution. So that's another good operator was developed. DeepONet was developed at Brown by a group. FNO was developed at Caltech, and these are sort of competing, but we will use them all. Okay, so this is a parenthesis because I want to go back and discover algorithms, and how do I do that? So let's look at the relaxation methods I told you about. So we start with trying to solve this PDE, and we discretize it, so we have a linear system. Even if it's a nonlinear PDE, eventually you end up with a linear system inside the Newton iteration. And then we find some increment, and then we have a correction, and then we iterate, and we have a loop here. So these are relaxation methods. These are the methods that I described to you earlier. Now, remember what's wrong with them? They converge, initially they converge very fast because they smooth the high frequencies, the errors, the high frequencies. But then the coarse components are the troublemakers, very, very, very slow convergence. So on the other hand, I told you that neural networks are very good with the coarse components. So I'm going to change what says standard solver. I'm going to change it with something else. I'm going to change it with the standard solver once in a while, and with a DeepONet that is pre-trained. Okay, so this way I will capture both. I will attack both the high frequencies and the low frequencies and the intermediate frequencies. Is that clear? So once in a while, so in here, when I come here, I will use my standard solver and do a loop. And then next time I may use the DeepONet, the neural network that gives me improvement on the course and so on. So I do a double punch, or one on low frequencies, one on high frequencies, and keep doing it. And it turns out that if you do that, it works really well. For the multigrid I told you about, it's the same thing, because at every level I will use that algorithm. Instead of just smoothing only the high frequency components. And in fact, I will not even need a very sophisticated grid, because I can use this. Okay, here's an example for the 1D Poisson equation, UXX equals 1, let's say. If I use Jacobi, as you can see here, this is the convergence versus iteration, really flat convergence. And look at the error, very, very big error. And the reason is we said is because it's a non-uniform convergence. The low modes are the troublemakers. The high modes converge very fast. If I initialize the network only with a DeepONet and then continue with Jacobi, still the problem. But if I alternate Jacobi, DeepONet, Jacobi, DeepONet, Jacobi, DeepONet, you can see here what the convergence is. And it didn't cost me anything, because I pre-trained totally my DeepONet. So Jacobi is known as embarrassingly parallel. It's so parallel that people forgotten about it until the parallel computers came to line, and they basically you can it's fully scalable. So you have this full scalability. You just need to go to a neural network from time to time to give you that extra information. So I just demonstrate that manually, how you can think to construct your own algorithms as meta solvers. So I have the solvers, and then I create a meta solver. We call it hints, and the reference is given here. So it's really simple, just by use some rationale. But we wanted to extend this to other solvers. It turns out that the more sophisticated solvers are these solvers called Krylov methods. If you've heard of conjugate gradient descent, stochastic gradient descent that is used in neural networks, these are all these Krylov methods, and many, many variations. Now you have this dilemma. You have a lot of relaxation methods, a lot of Krylov methods, and you have lots of neural operators. How do you combine them? So I gave you one example that a graduate student had patience to do that, but how do you actually do it? Can you do it automatically? That's my next question. So Krylov methods, just so that for a reference, again, they have the problem of, they use preconditioners, but the problem is the coarse preconditioner. How do you build the coarse preconditioner or the high frequency? And the coarse preconditioner, again, will come from a neural network, will come from a neural operator. Same idea. In particular, I will use the trunk basis of the depot net to produce a basis, which will be my preconditioner that is shown here on M. Remember, I use M to have the preconditioner. So the preconditioner will be discovered automatically through a neural network, which then I will use it here. But again, so I have a new approach, and the new questions are hybrid solvers. I'm talking about always better. How much improvement can we obtain? And what is the optimal solver? So we have shown that this approach can produce the fastest solvers on Earth. We don't know other planets. And so the hybrid solvers are always better. For example, in this case where we do a 3D scattering problem, which I will show you later, it's the error versus number of iterations. You see for that scattering problem, you have some negative eigenvalues. So you can see the relaxation, all relaxation methods, no matter what, they diverge. But with the neural operator, they converge. The Krylov methods are faster here, but with a depot net, you can make them even faster. So always win without paying an extra cost. That's so important. In terms of iterations, you can see here we go from 791 iterations to 2 iterations. That's sort of from 791 iterations to 14 iterations for the same method. If I use Bayes' stub, which is like a gradient descent method, I go from 791 iterations to 14 iterations, from over 1,000 iterations to 19 iterations. But we're not talking about small improvements. We're talking about huge improvements, big breakthroughs. The industry is using it. ANSYS is the biggest software company in the world. So here, they're solving solid mechanics problem. Notice that DeepONet is trained in this geometry, and then it's used in another geometry. So in other words, when you change geometry, when you change problem, if this geometry is relatively, like here, for example, axisymmetric, this one's axisymmetric, but different domains, you don't have to retrain it because you just want to have the coarse modes captured, the coarse solution. That's very important. And in fact, so you can see here, this is ANSYS, the state of the art in solvers for commercial computations. And the hints is down here, 3 to 4 times faster. There's also more recent developments that is. Okay, so I want to present now Omega, and Omega stands for Optimal Meta Solvers via Generative Artificial Intelligence and Differential Games. It's a DARPA program that we currently have. It's called Disruptioneering Program from DARPA because it's disruptive engineering, disruptioneering. I didn't come up with the term, the DARPA people. Okay. So we want to discover what I told you. I want to discover that automatically so you don't have to think about it. Okay. So if you didn't understand anything, don't worry about it because this will do it automatically. So just click a button and it'll do it, okay? Just kidding. All right, so, but we said we have 2 types of classes. We have lots of operators for low frequencies, and I have to choose from there. And then I have a lot of existing solvers, everything that has been developed, everything in the books. So imagine you have your ChatGPT learning this and learning that, learning relaxation methods and learning all these operators. And then you want to combine them, but which combination is the best? Because there's so much parameterization in each one of them, right? Just for a single neural network, you have the neurons, you have learning rates, you have depth, and so on. The same thing for the relaxation methods. You have the relaxation parameter, then you have what type of relaxation method, you have symmetry, you don't have symmetry, and so on. Should I use Krylov methods or should I use relaxation methods? So there's lots of options, but we're gonna do that, we're gonna do an optimization. So we're gonna do an optimization. So we're going to parameterize all these. Some of them are sort of categorical data, but we can parameterize them with numbers. But let's say you have to sort of define first what is optimal, what is best, because you may be best in something, somebody else is best in something else. So here we're talking about optimization in high dimensions. we want to reduce the computational time, we want to reduce the error, we want to reduce the number of iterations, we want to make this parallel, we want to also reduce the memory. So I have a multi-objective optimization, right? I don't have just one objective, because if you're an academic, you like accuracy. If you're industry, you like speed. If you're somewhere in between, you have a different preference function. So in fact, that's what I want to show you, that there's no such a thing as best, but you can use a preference function, and with respect to the preference function, you can find a unique solution. Otherwise, you will find this Pareto front. For example, here I have, let's say we have only speed and error, computational time and error. So you do many solvers, and you find all these points, blue and red. But only there's this line that I call the Pareto front, the yellow line, that is really the one that satisfies both criteria at the same time, right? It has the smallest F2, the relative error, and then the smaller F1. So if you're not familiar with the Pareto front that is used in design, it's basically the lower surface, because it's high dimensions, it's a surface. In fact, it would be a non-convex surface. It makes things more interesting. So if we find that Pareto front, it's the beginning, but I still don't have what is best, because you have to define what is the best. User has to define. So you have to give me your preference function, then I will take your preference function, I will create a surface, and I will cut the Pareto front with that surface. Is that clear? So then I have unique solution. So I formalize this problem, and I will do that both for relaxation methods and fill-off methods. Now, here, the reason I have this list is because to show you that X1, my variable, will be from this pool of different operators. So I have 1, 2, 3 different, it doesn't matter if you don't know the operators. The only thing I want to say something about KAN is a new type of network. It's called Kolmogorov-Arnold network. It doesn't use MLP, it uses, here, for example, it uses Chebyshev polynomials. But anyway, these are operators, as described. X2 will be what type of relaxation method? So here I have 4 of them. Successive over relaxation and symmetric successive over relaxation, the one that I didn't talk about. And then how often you go to the neural network, how often you go to the standard solver. It turns out that you don't need to go to neural network very often, so you go once in a while, and that ratio parameterizes this. And then there's another parameter that tells you how many levels of multigrid you will do, and so on. Here, in Krylov methods, it's a little different, but same idea. You have variables that parameterize all the inputs that you can think of. For example, strategies of how you apply the smoother, how many times you use the DeepONet, how many levels of multigrid. So, but these are now parameters that you have as inputs to the optimization. So here's the optimization, the multi-objective. The MU stands for multi-objective optimization. The performance metrics are a 7-dimensional space, have the computational time, convergence rates, all the way to MAC stands for multiplies and accumulated sums, relative error allocation. Basically, you can add to that list, but this is a pretty good list to start with. And now we have to optimize in 7-dimensional space, not just in 2-dimensional space that I had in the sketch before. So we want to minimize all this vector of f of x, and I want to minimize, but as I said, this problem has many solutions. If you bring in your preference function, which will say, I want 30% to be fast, 40% to be memory, and some linear combination. So you take a preference function and you write it as you compose it with these measures, and then you have something which is a sum of lambda i's, fi's. So fi's are these measures with respect to which you optimize, and your preference will be defined by the lambda i's, which are coefficients. For example, if you take lambda I equals 1, then you only care about the error. If you take lambda 2 equals 1 and everything else 0, then you only care about speed. But of course, you may be interested in something in between, because you have to compromise sometimes. So in this form now, we have a unique solution. In fact, we can write the whole problem as a linear programming problem, where we minimize. So now we have this with respect to lambda, which is the preference function. We minimize this vector f, the 7-dimensional vector. And it's a standard linear programming that you use a existing tool solve this problem where you have the sum of lambda i's is equal to 1. Again, lambda i's relate to the preference. So schematically, what you will have is here on the left. So here, the dimensional space is 7-dimensional, but here I just use 2 dimensions to illustrate the point. So you have the Pareto front, is the red line. That's where all the good solutions are. And now, which one matches your criterion? Well, if you use preference function P2, this will be this one, for example. Preference function of 1 that emphasizes speed versus error. This will be another one. So where you cut it, okay? So very simple. This all complex thing now comes down to linear programming, which we can use MATLAB to solve. Now, so this is a sketch on the left. It looks very smooth. On the right, you have all these blue points. These are all pre-computed. And now you find the red points, which are this front, and then you have a certain preference function. I'll talk more about preference functions. Here, you can cut it here or there, and you find the solutions. Hope that's clear because it's really simple. I created a Pareto front. All the good stuff is there. Now, I go back to me, the user, my preference functions. I create new surfaces, and I look at intersection of surfaces. Is that clear? Okay, so let's look at this 3D problem. Sometimes you are interested in checking if you can detect things like a submarine for certain applications from scattering. Difficult problem. I have this equation here, the Helmholtz equation, very complex boundary conditions. The whole thing has to be done complex arithmetic. We generate data, and we train a neural operator without a scatterer. Just a neural operator would know how to solve this in no time, in real time. But there will be no scatterer there. Remember, I'm not interested in the details. I'm interested in some characteristics with the low frequencies from the neural operator, because the rest I will do it with the standard solvers. Okay, so this shows how you actually train the neural network without any scatterer, and then I can extrapolate to a scatterer, which is a cube, or a submarine, or a sphere, and so on, because I'm trying to detect that. So that's the problem, and here's the answer if you do the Pareto fronts, different visualizations. I have 7-dimensional space. I only use 3 dimensions here to project, and you can see where the red points are. The red points are basically the ones that satisfy the Pareto front in here, computational time, relative error, number of iterations. Here's a different, I use the number of operations as an axis, so you can see it doesn't have to be a continuous surface, by the way. So what do we find? Let's say the preference function P1 is the average of all performance metrics. So you don't want to go for speed, you want to compromise. So that's a conservative user who takes something like that. And in this case, you find, for example, these tables tell you the algorithm that you developed automatically. In other words, for a neural operator, you have to use DeepONet. For classical solver, you have to use this flexible by CG stub. How many grids? How many levels of grid for the multi-grid? 2. What smoother you should use a relaxation, and then strategies. I use 3 smoothers, 1 DeepONet, back 3 smoother again, because you smooth before and after the coarse graining operation. And then you can see that's going to be the idea. The idea is that you solve a problem like that. You can have a different preference function, P2. You weigh things differently. And now you find, for example, here, you find the flexible GMRS. And then you find Jacobi Can as a neural operator. Now, it will be very, very difficult for you manually to do that. But you can prove, and that's all these tables there, the numbers are, you can prove that indeed this is really the best optimal solver for those conditions using this preference function. If I use a preference function that has only F2, let's say the F2 is the computational time, I will find something totally different. Now, to show you that this applies to different problems, this is a problem from ANSYS again. They are looking at power electronics. This is from a GPU. They're looking at structural integrity. And here they're using this preference function P2. You can see this combination. Again, you find Pareto front, and then here's the speed up. The speed up is something that similar to what I told you earlier. It's a very, very large speed up in terms of iterations and at least a factor of 10 times of the computation time. So I talked about algorithms. Of course, this is not limited to linear systems, or we've done for nonlinear PDs and so on. But you can basically, the message is that with the existing algorithms out there, you can make lots of combinations where you can create meta solvers, and turns out that these meta solvers are good because you can tackle uniform convergence. And most of the solvers are inadequate because they exhibit non-uniform convergence. Yes.
I have a question. From what you were describing just before that sometimes you have a primary objective, like let's say speed or computation or whatever, or maybe a couple of them. But there are situations where you find that a little bit of like diminishing one aspect a little bit gives you a huge benefit of another parameter that you are interested in. Is this methodology capable of teasing this kind of?
Yeah, very good question, because here I show you linear preference functions, but you can have nonlinear preference functions with an if statement. For example, I'm interested, let's say I'm an engineer. I'm interested in, if I get 10% accuracy, I'm good enough. Now I go for speed. So that's, you create a nonlinear function like that, and that will actually give you exactly what you want, because there's a sort of a jump, like you said, from the performance. But so you can, from some observation that you have, you can encode that into your preference function. In fact, nonlinear, the way to use this is with these nonlinear functions, because you may not want to go 10 to the -7 accuracy and change for that. Or you can put a bound on the time or the memory, because if you cannot fit the problem in the system, you cannot solve it. So that becomes another if statement. So you can have sort of this broken composite preference function. So the preference function is where you encode that type of information. I haven't done exactly what you're saying, so that's why I cannot be more precise. But we have done something similar that I didn't show here. Okay, so a big problem in neural networks is even if you know the type of architecture, I want to use a CNN, how many layers, what's the pooling, what activation functions, and so on. So this parameterization. So this, of course, has been recognized by the community. So in the last 10 years, there have been a lot of this area, is a whole area, NAS, neural architecture search. So basically, you have a calligraphic A space, that's your search space. Then you have some sort of strategy. You take out one, you try it, you see what type of performance and trends you have, and then you go back. There are tools by Microsoft like AutoML. If you ever use AutoML, it's basically an NAS. So this will find the best architecture. But now imagine imagine the following problem. And I see at least one paper per day on this topic. Forecasting time series, okay? In fact, Meta had a couple of years ago, a product called Profit. They wanted to predict what's going to happen with sales at Christmas, so Profit. And they were using some, I think, an RNN type architectures. So recurrent neural networks. But it's a zoo out there. There's many, many different architectures, CNNs, RNNs, LSTM, GRUs, and how do you combine them? And now the transformers, from ChatGPT made transformers very famous, or transformers made ChatGPT famous, depending on your point of view. But now transformer is not the latest and greatest. Mamba is like state space models. For those who are electrical engineers, you probably know state space models because they are linear models, but these computer scientists made them nonlinear, and they work better than transformers now. So every day there's a new architecture and competing. And so to this day, you will probably find at least a few thousand papers that say that for time series, they don't specify what, time series forecasting. Imagine you forecast diabetes, for example, right? You take glucose and you forecast diabetes. This architecture is best, LSTM, this architecture is best. And you will see today that there's no such a thing as best architecture. Only for that paper that they wrote is good. You go to slightly different data for the same problem, different patient, for example, diabetes, it's totally off. It's not the best architecture, so nobody can guarantee this. So as I said, an example in the past, what they would do, very, very expensive, do hyperparameter tuning or building up a very big neural network and then prune it, like you prune the bushes in the garden. You prune, you cut down. It's a very, very expensive operation. If you use AutoML, as I said, or other type of tools, you will see it's very expensive. So what architecture? I just told you, even for time series, here I have a list of different architectures. For example, LSTM, was developed in the 90s, still probably is the default neural network for time series forecasting for dynamical systems, okay? Or lump systems, ODEs and so on. GRUs is a simplified version of LSTM. Instead of 5 gates, they have 3 gates. The encoder decoder on the right is a transformer that's used in ChatGPT. And then what I told you, the SSM, the state space model, or it's called Mamba because of the implementation developed at Stanford by making a linear state space model. It's the same that in Kalman filtering, similar idea. They make it nonlinear by using activation functions. I will show you some more details later. So actually here. So the idea, here's the idea again. Just like before we took several components and we built a composite algorithm, MetaSolver, now I will have a composite architecture. I will pretend I don't know what it, of course I don't. So I will take some modules of transformer, GRU, LSTM. I will take 3 of them, 5 of them, but I don't specify the number. But I take N GRUs, M LSTM, J attention stands for transformer, and then K SSM. Do you understand what I'm doing? I don't specify the number, so it will come out. That would. Now, you ask me, how do you know the sequence? I'm not going to specify the sequence either. I will parameterize it, so I will find the number of modules that I need, could be 0, and then I will find the sequence. So which one will go first, second? So I go from bottom, which is the input, to the top, okay? And now between there, I have some linear layers and so on, but never mind the, so the idea is exactly the same. I'm gonna do it offline. So I'm gonna come up with a optimum Pareto front, and then based on a preference function, I'll choose the best architecture for time series forecasting. And we have done for various applications, but I'll only show you the first application will relate to the biomedical application of glucose trajectory. So talking about glucose trajectory, these are real data, real patients. So what we'll be doing is we will, it's very important to sort of prognose even half an hour ahead of an event like hypoglycemia, glycemia or hyperglycemia. It's very important. So here we're trying to do 2 hours prediction by looking at the history. So you have seen these monitors that they use for glucose monitor. So you have that, and then you can predict what's going to happen in the next couple of hours. Should I eat a tiramisu or not? That's the question. So, okay, so parameterization, how we do it? Well, X1 will give us how many of each architecture would take. I take from 0 to 2. You can extend that, of course, but this is a proof of concept. Then I have another variable X2, which will give me a sequence. SSM first, transformer, GRU, or LSTM, any combination. You just took a few, but you don't have to be so exhaustive, but you can exhaust it. And you can have more variables. Here I just keep 3 variables, but X3, for example, will be on the size of the transformer, or the number of neurons, something that characterizes the architecture, but you can imagine you can have X3, X4, X5, and so on for the details of individual architecture. So you don't use a monolithic architecture, you can also parameterize the block itself. And then you have the composites. And then the preference functions here, P1 will be some average, P2 will give you the accuracy, P3 is the training cost, and then you can have a mixed. So again, this table shows what we get for the problem I described from the Pareto front. So if you go with a P1, which we just said that P1 is the average for the conservative, you find that if you need a GRU and then LSTM, that will give you the best architecture. If you go with a P2. Let's go see what P2 is. If you go for accuracy, you have a very complicated architecture. 2 GRUs units, 1 SSM, 1 transformer, and 1 LSTM in that order. If you go for cost, just the GRU is good enough. So you can find the one module only. And then the last one was some other. So basically, you construct this architecture just solving a linear programming problem in this particular case. Depending on the preference function. So this is what I'm saying. For the same problem and the same data, I found 4 different architectures. The question is, of course, if this generalizes to other patients, so you don't have to retrain. The answer is yes. If these patients have the same sort of characteristics, actually, you don't have to retrain, so that's a plus. But if you try to apply this to something else, for example, in a physical problem or commercial machine learning problem, you need you need a different architecture. In other words, all these people who say they have the best forecasting to forecast everything, it's totally not true, because how you forecast sales in shoes is very different than sales in something else and so on. Even in commercial machine learning, this proves that. But certainly we found that depending on the problem, that's why we look at 4 different categories of problems. We found that the type of problem, the physics and so on behind the problem is really what defines, and then the preference function. That defines the Pareto front. Preference function defines which point from the Pareto front you will obtain. The other question is, can you solve the inverse problem? In other words, can you find the preference function? If you give me an architecture and say, run this, can you tell me what this architecture is best for? Okay, find the preference function. And the answer is yes, you can find basically these coefficients, lambda 1, lambda 2, lambda 3. And from there, like for example, here, this architecture here at the end gives you lambda 1, which I forgot exactly, multiplied by error. So that will be the most accurate architecture, because lambda 1 multiplies F1, which is the error, and then the rest is 0. So you can solve also. So if somebody gives you an architecture now, you can tell, well, this is good for this preference function. But if I want speed, it's not going to do it for me. So it sort of dissects really the use of architectures. Okay, so I basically done. I wanted to communicate this point that there is hope now that in addition to discovering your own equations, you can also discover your new algorithms and also discover new architectures. And this is solved with a simple problem that the way we turn the multi-objective optimization composed with the Pareto front with a preference function that gave us some unique architectures. Now I didn't tell you about the most interesting part, which is, although I already showed this type of schedules, you can see this is a non-convex function. So linear programming will not capture, for example, this part here, as I show here on the right. So turns out that quite a few of the algorithms, some of the best algorithms are hidden in that non-convex part. And it's very difficult, of course. There's no guarantees, there are no theoretical guarantees that we can find global minima of non-convex functions. So how do you do it? So we are working on something called differential games, which allow us to actually go also in that regime. And in some of the cases that we've done, 30% of good algorithms were also there. So that's sort of the future direction. So just as a advertisement, my work is supported by CCROGS, for Physics and for Machine Intelligence, is a center that I direct for Pacific Northwest National Lab. And you can see what we emphasize operators, and then additional graph neural networks and spiking neural networks, which resemble more like bioplausible solutions to neural networks, and also by MNURI, which is called learning and meta-learning PDEs via pins and other neural networks.